All of the matter and energy that constitute the current universe, visible and invisible, is collapsed to a point that isn't even a pinpoint. It's infinitely small and infinitely dense. And there's a cataclysmic explosion. That's the Big Bang. That's still part of the standard cosmological model, still an accepted. The difference between the early periods that you just described, maybe even in terms of fundamental cosmological laws, and later periods. Now, we might also throw in this caveat too, is that as far as I've been able to determine, it's still axiomatic presupposition among scientists that the laws of physics that obtained at the point of the singularity are not the same laws of physics, or at least can't be shown to be, that govern the universe as it's currently unfolding.
It's actually better to start not with the beginning, which is ambiguous, which is hotly debated, which is contestable, and those are all good things about the scientific process, but actually to start with today. So let's go back from today, when we think we understand the laws of physics that are presented to us, and go back in time to a point before which we don't understand the laws of nature. Because if you start from a point of ambiguity and uncertainty, and then you attempt to extrapolate forward, you're less likely to get the right answer than if you kind of go back historically and ask, when do we lose sight of the plot line? When do we lack our understanding of the laws of nature? So starting from today, we see four forces of nature. There's two nuclear forces called the strong and weak force that govern the behavior of atoms and radioactive decay. And then there's the law of electricity and magnetism that govern everything from electromagnetic communication, like we're doing right now, to refrigerator magnets, to magnetic levitation and future hopeful transportation mechanisms. And then there's the law of gravity, which is perhaps most familiar to us when we try to get out of bed every morning. We're fighting against the entire mass of the Earth with our meager masses, hopefully maintaining the battle every day to get out of bed and make your bed in the morning. These four phenomena are familiar to us. And we can actually go back a great distance in time, and even staying only in space where we are right now. Let's take the Earth back in time. We go back 4 billion years. The Earth condensed out of the shrapnel of a supernova that had exploded perhaps 1 billion years before that in our local arm of the Milky Way galaxy. Let's go back a few more billion years. The dark energy that we spoke about earlier began to dominate, and the universe started to accelerate faster and faster. Well, that still is in the laws of classical physics and quantum physics that we understand. Let's keep going back. Now we're back, say, 10 billion years ago. The first stars that were ever made are all long gone. They've all blown up into these population 3 events that the Webb telescope is hopefully going to shed more infrared light on. And then you go back even further, 100 million years before that. So now you're going back from 13.8 billion years. Let's say today we're talking on a Friday. But you go back, there's some Friday 13.8 billion years ago. If you just kept going back 7 times 24 and you just keep counting the weeks and the years and the months, you'll reach some day. And there'll be some day that 3 minutes earlier, the laws of physics that we really understand, know, and love, gravity, electromagnetism, the strong and weak nuclear forces, that they all froze into the configuration that we can understand today.